Welcome back to part 3 of our Three.js tutorial series. Last time we covered geometry and materials and left off with this scene. Today we're going to take this scene to the next level with our own custom materials. Just to get you up to speed with how we arrived at this scene, we created a large sphere ensuring to encompass the camera so that we would be looking at it from the inside. We also textured it with this image of the Milky Way galaxy, and that's how we got the star field. We then took a smaller sphere and textured it with a world map, a larger sphere for the clouds, and then a transparent sphere for the atmosphere. The star field looks great, but the Earth is not yet looking amazing. We're going to use custom materials to take it to the next level. As we described in the previous video, materials are essentially small programs called shaders that run on the GPU and control how objects are rendered. Shaders are responsible for transforming raw vertex data into the final image that you can see on the screen, and they can be customized to achieve a wide range of visual effects. There are two types of shaders that we are interested in. That's the vertex shader and the fragment shader. Here's an example of each. They are written in a programming language called OpenGL Shading Language, or GLSL for short. GLSL is a high-level language similar to C in syntax and structure, but specifically designed for the kind of mathematical operations that are common in computer graphics. GLSL is statically and strongly typed, meaning every variable has a fixed type determined at compile time. We therefore have to specify the data type of variables during declaration. If it's a boolean, then you can use bool. Signed integers are ints, and unsigned integers are uints. You also have floats for single precision. You can also create vectors, matrices, and arrays from these simpler data types. So for example, to create a three-dimensional vector using floats, you can declare the variable as a vec3. 4x4 matrices whose components are floats can be declared as mat4. And this is how you would create an array of floating point numbers. Samplers are used to store texture data, and so if you want to pass an image into a shader, this is the data type to use. The main method is the entry point for your program, and so it must be present. There are many built-in functions for things like trigonometry, dot product, and so on. But if you want to create your own functions, ensure they come before main. Also, don't forget to declare the return type. Every sphere that goes into making the Earth as well as the Sun are all going to have separate vertex and fragment shader pairs. Let's begin by looking at how we would create the surface of the Earth using these shaders. Let's begin by creating the vertex and fragment shader files. If you want VS Code language support for GLSL, you can check out the extension WebGL GLSL editor. You get features like syntax highlighting, IntelliSense, formatting, and so on. You're also going to need to install Vite plugin GLSL library so that Vite knows how to handle GLSL files. Also, create a file in the root directory called vite.config.js and add this code. We can now import the shader files in our main.js without problems. Let's also create a sphere for the surface of the Earth. And now, instead of the built-in materials, we use shader material. Shader material is used when you want to create a custom material. The constructor takes an object, and we can use it to set the fragment and vertex shaders. So let's go ahead and start editing the vertex shader. In part 2 of this series, we discussed vertex attributes like color, position, UV coordinates, and surface normal. Three.js is going to take care of injecting these attributes into the vertex shader. The thing to keep in mind when working with the vertex shader is that you're dealing with individual vertices. So for example, position attribute is for a specific vertex. Let's go ahead and use it to calculate the position of the current vertex on the screen. The GL position variable is built into GLSL and is used to specify the output position of the vertex. Every vertex shader must set this variable. The position variable contains the 3D position of the vertex. This part creates a 4D vector from the 3D position vector. This 4D vector is then multiplied by the model view matrix and projection matrix to obtain the final output position. The projection matrix and model view matrix variables are also injected by Three.js. These matrices are used to transform the 3D position of the vertex into 2D screen coordinates. The model view matrix is actually a combination of two matrices, a model and view matrices. If an object in your scene is parented by another, as was the case with certain strings, the child is in the coordinate system of its parent called local space. Model matrix will transform the child from local space to world space so that it's in the same coordinate system as its parent. The view matrix is used to transform the vertex from world coordinate system to the camera coordinate system, so it will take care of things like the camera's orientation and position. The projection matrix is used to map the 3D coordinates of the vertex into a 2D plane, which can then be displayed on the screen. Over to the fragment shader now, and the fragment shader deals with individual pixels. Just like GL position on the vertex shader, GL frag color is a built-in variable in GLSL that is used to specify the output color of the pixel. Every fragment shader must set this variable. This part creates a 4D vector that represents the color blue. The first three components of the vector represent the red, green, and blue color channels respectively, and the fourth component represents the alpha channel. With this code, this is what you get on the browser. It looks like a circle due to the uniform color, but it's actually a sphere. This is the equivalent of using mesh basic material on a sphere with the color property set to blue. Let's make things a little bit more interesting by taking light into account. And the way we are going to approach this is by simulating two components of light, diffuse and specular. Diffuse light makes the surface of an object brighter the more it faces the light source. The specular highlight, on the other hand, is going to be brightest on the surface that reflects light directly towards the camera. So we're going to need to know the surface normal of the current pixel. But vertex attributes are in the vertex shader. To pass the surface normal to the fragment shader, we declare it as a varying variable in both vertex and fragment shaders. And then in the main method of the vertex shader, we set its value. We multiply the surface normal with model matrix to ensure that any transformations applied to the object also apply to the normal vector. Surface normal vector is 3-dimensional, while model matrix is a 4x4 matrix. So we need to convert to a 3x3 model matrix. Let's also bring in pixel position in the same way. We also need to inject light direction from JavaScript. This is made possible using uniform variables. Let's declare a light direction variable as a uniform in the fragment shader. Then in JavaScript, in the constructor object of our shader material, we're going to create a uniform property and assign an object to it. In this new object, we are going to create a light direction property, which will now contain a normalized vector that represents the direction of light. This light direction property has to be named exactly the same as the light direction uniform in the fragment shader. We now have all the data we need to simulate light. Let me write all the code and then go through it. One thing that I want to point out is that this is one of many ways of simulating light, and the numbers I'm using are not set in stone. Feel free to tweak the code or use different values to see what you get. So we begin by declaring the diffuse color, blue in this case. Then we find the dot product between the pixel normal and light direction. The dot product is used to determine how aligned two vectors are. If the vectors are normalized, then you get a value between -1 and 1. If the two vectors point in opposite direction, the dot product is -1, and 1 if the vectors point in the same direction. We reverse the sign to ensure the illumination is on the right side of the sphere. This max function returns the greater between dot product and 0, and we are using it to ensure no negative values. We then get the diffuse color by multiplying max dot product by diffuse color. This has the effect of accentuating diffuse color in regions where the value of max dot product is high. For the specular highlights, we begin by creating two variables, shininess and specular strength. We then create a normalized view direction variable from the camera to the pixel position. And this camera position variable is available in Three.js, so we don't have to bring it in ourselves. This reflect function is going to give us a new vector that represents light direction that has been bounced off a surface with this normal vector. We then need to see how aligned the reflected light is to the new direction. To avoid negative values, we again use the max function before finally raising the result by shininess value. And this is what will bring out the shiny specular spots. Let's also go ahead and pick a specular color, and I went with this kind of a yellow-orange color. Then we just multiply spec by specular color and specular strength. This specular strength variable will help you control how prominent the specular highlight is. Let us now combine diffuse and specular and use it to create a 4-dimensional color vector with no opacity, and we end up with this result. Great. Now is a good time to start bringing in images as uniforms. And as I mentioned, we use sampler2d variable to hold image data. On the JavaScript side, ensure you've imported the images and then use texture loader to add them to your uniforms. Let's also bring in UVs from our vertex shader. UVs contain information about what part of an image the current pixel corresponds to. The first thing we're going to do is swap the diffuse color with the world map. To extract color information from the part of the image that corresponds to the current pixel, we use texture2d function supplying the world map and UV coordinates. This returns a 4-dimensional vector containing red, green, blue, and alpha channel values for the target pixel. We can convert it to a 3-dimensional vector, dropping the alpha channel like so. We also need to set the specular strength to the values in our specular map. As we pointed out in part 2, the specular map is a grayscale image, and so you can use any channel except alpha. I went with red and multiplied it by 2 to make it more prominent. Let us give it more character with a normal map, as it currently looks like an inflated balloon. A normal map tells us how to perturb the surface normal vector, which changes the way light interacts with the surface, creating the illusion of surface details like bumps, stretches, wrinkles, and so forth that would be too small or complex to model explicitly using geometry. We're going to use a function which takes the normal as an argument and performs the perturbation. I'm not going to get into the details of how this function works, except that it takes the surface normal, changes its direction using the normal map, and returns the result. We can then use the result in place of the vNormal variable. As you can see, the earth is now more detailed. The next thing we need to do is work on night lights. There is a built-in interpolation function in GLSL called SmoothStep. This function takes 3 arguments, edge 0, edge 1, and x. The first and second arguments define the range within which the interpolation occurs, and the third is the input value to be interpolated. The SmoothStep function returns a value of 0 when x is less than the first argument, a value of 1 when x is greater than the second argument, and a smooth interpolation between 0 and 1 when x is within the range defined by the first and second arguments. So if the dot product is below negative 0.05, it returns 0, and 1 if the dot product is above 0.05. If the dot product is between negative 0.05 and 0.05, it will be mapped to a value between 0 and 1. I found the range between negative 0.05 and 0.05 suitable for creating the twilight zone, instead of a hard edge. The way we decide whether to show the day, twilight, or night side is by using a built-in function called mix. It takes two vectors and an interpolation factor. It then performs a component-wise linear interpolation between the two vectors based on the interpolation factor. So if the interpolation factor is 0, you get vector 1, and vector 2 if the interpolation factor is 1. It will blend the two vectors if the interpolation factor is between 0 and 1, shifting weight between vectors 1 and 2 for values from 0 to 1, creating a nice twilight. Let's now go ahead and create cloud cover. Clouds are going to be a separate object because we want them to hover over the Earth. The object is a slightly bigger sphere with its own vertex and fragment shaders. Don't forget to set the material as transparent and double-sided. We're also going to use uniforms to bring in the cloud image into a fragment shader. The vertex shader is no different from what we've already done. In the fragment shader, we still need to do some lighting calculations because we do not want the clouds to appear on the night side. We're only going to compute the diffuse components, setting the diffuse color to the cloud texture. Notice the clouds are lacking depth. This is because they are not casting a shadow. In the fragment shade of the Earth, we are going to deduct the cloud texture alpha channel from the specular strength. And now you have a shadow where the specular highlight is. The last thing we need to do is add an atmosphere. This one is also a separate object with its own fragment and vertex shaders. The material is transparent and we are going to need light direction uniform again. Let's also go ahead and pass pixel position and surface normal from the vertex shader to the fragment shader. In the fragment shader, we set a color for the atmosphere, so blue, and again we perform lighting calculations to ensure atmosphere is only visible on the day side. This part is there to ensure we only have atmosphere around the edges and not the part facing us directly. And this adds a little fuzziness to the extreme edges. If we now use atmosphere color as the R, G, and B values, and then multiply max.product by edge.product and fuzziness, we get this. So now the only thing remaining is the sun. The sun is slightly unique. This time we are going to create custom geometry with only one vertex. You can check out part 2 if you'd like details on how to create custom geometries. We also create a new shader material, supplying the fragment and vertex shaders for the sun and not forgetting to make it transparent. Then instead of a mesh, this time we are going to create points. A point is essentially a square located at the vertex position and is always facing the camera. We're going to play with colors in the fragment shader to create the illusion of the sun. Let's also move the sun away from the Earth and add it to the scene. The vertex shader is straightforward. We just set the point size to something large. 500,000 will do, and the calculation for position is as we've done before. The fragment shader is where we get creative. Keep in mind we are dealing with individual pixels within the square. To get the current pixel coordinates, we use GL point code variable, which is built in. The center of the square has the coordinates 0.5, 0.5, and so we can calculate the distance from the center like this. We also double the distance to increase the range of the radiant effect. Let's also choose a color for the sun, and I went with this dull orange color. Here we calculate the base color of the current fragment based on its distance from the center. The closer the fragment is to the center, the brighter it will be. Then we modify the color of the current fragment by multiplying it by the original color of the sun and increasing the intensity. Here we are calculating the factor that will be used to adjust the alpha channel of the color based on the distance from the center. The main function is going to ensure that the alpha channel does not exceed 1. Finally, this line sets the color of the current fragments to the calculated color. And there you have it, guys. Hope you enjoyed the tutorial. My name is Francis, wishing you happy coding, and I'll see you in the next one.